Schrodinger wave equation is the main focus for today's class. So let us do it. So for this time independent Schrodinger wave equation, there are two ways to derive it. Both the ways we will look at it. There are two methods to derive the time independent Schrodinger wave equation. As the name is stating, the wave equation we will be having, it will not be dependent on time. And it's a very important discussion which we are doing.
Okay, sir.
Time independent Schrodinger wave equation. Time independent Schrodinger wave equation. Now see, let us look at the method one to derive the equation. We will be starting with the wave function. We know that psi, which is the wave function, it is a function of position and time. It is given by A, E, I, kx minus omega t. So we have to start from here. Now what I can do, this wave function, which is known to me, I can like write it in this way. A, E, I, kx dot E, I or minus I omega t, isn't it?
Yes, sir.
A, E, I, kx dot e to the power of minus I omega t. Now what I can do is that here I have two terms. One is the position and one is the time, like x and t. So I can mention that this is the position term, this is the time term. Isn't it? Like this is position dependent. This is time dependent. Okay. Now the position dependent term, we can replace it with a different constant. Uh, like I'm replacing it with a function, which I'm calling it as phi x. So definitely this position dependent term which we have, I am replacing it with phi x. So here it is understood that in later part of the derivation, I will be writing phi x instead of a e I k x. So I will be substituting a e to the power of I k x with phi x, and this phi x represents the function of position. And what this is what this term is. This term is the function of position. With different values of x, I will get different values of phi. So this is clear. So after plugging this, we will get a refined wave function which will look something like this. Psi, which is the wave function, which is a function of position and time. The position dependent term that I can write phi x, and the time dependent term I can write it as it is. I can write it as it is, like whatever is there, e to the power of minus I omega. Now what I will do? Now I will apply some mathematics, because now I have a proper wave function using which I can get to the Schrodinger wave equation using this. And how we will achieve there, we will go there. Let us try it. Now I will be differentiating both the sides of this equation with respect to time. Differentiating both sides with respect to time. Isn't it? Now, if we do that, let us see what we will get. So here, since it's a function of two variables, we have to do the partial derivative with respect to time. It will be psi itself, the function itself. This will be equal to, since we are differentiating the function with respect to time, this phi x will be treated as constant, because the x will be treated as constant, because here the time t is the variable. So this phi x I can take outside, like nothing will happen to it. This will be the independent of time. And this term, when I will differentiate it, I will get minus I omega into e to the power of the same, minus I omega. Okay. E to the power of minus I omega t multiplied by minus I omega. This is what I will get after differentiation. Okay. Now what I will do is, the equation, the main equation, I will differentiate the both side with respect to x. I will differentiate both sides with respect to x here. Differentiating both sides with respect to x. Then you will get phi omega by phi x. The wave function we are differentiating it with respect to x. Now in the right hand side, this phi x we have to differentiate it, but this time term, it will be treated as constant. So this I can write it somewhere here separately because it will be, but time is constant now. I am differentiating it with respect to x, and this will become partial derivative with respect to x phi. So phi, the function which is dependent on the x, this will get differentiated with respect to x. Now I can do, I have to do one more differentiation, double differentiation here. That I can do. If I differentiate it one more time, this time term is constant, nothing will happen. It will be as it is. It will be as it is. But this term, it will get differentiated one more time. This term, it will get differentiated one more time. So I got this. Let, let me bring closer so that everything gets in one frame, easy to read. Yeah. Until here, everything is clear to us. Now the same the concept we can apply, which we applied during the earlier derivation, the conservation of energy. Like the total energy of the system will be the kinetic energy plus potential energy. And why potential energy is acting? Because the particle which we are considering, it is bounded by a force. It is not independent. It is not free. It is bounded by a force. And whenever a particle is bounded by a force, it contains, it possesses some potential energy because it is inside a field. So I know that total kinetic energy, like total energy is kinetic energy plus potential energy. Total energy, I can just write it with E also. It is fine. The representation. Okay. Now what I will do, I will just multiply both the sides with the wave function psi. It will become E into psi is equal to kinetic energy plus potential energy into psi. Psi means psi, the spelling psi. This wave function, we call it psi. Okay, this is clear. Now what I can do, this kinetic energy plus potential energy that I am having, I can give it a name and I can call it Hamiltonian operator. This thing, I can give it a name H cap. And this H cap is a special operator which is called as Hamiltonian. Hamiltonian. Operator. Hamiltonian operator. So what it will become after substituting, I can write something like this. This equation, it will become E is the total energy into wave function, that is the psi. It will be equal to the Hamiltonian operator, which I will write like this: H cap into the psi. Isn't it? This we will. So until here, the things are getting bit clear.
Yes, sir.
Yeah. Now we will write the final step. Like now what I will do, whatever equations I got earlier, like I will mark it. This one, sorry, this, uh, yeah, this equation and this double square equation. So the idea is that now we have the wave function. We will use this wave function, this equation, and we can substitute appropriately the values which we are getting, and we will do that. I will do it, then I will show it how I did it. So first let me write the equation, then we will look at it how I did it. So final equation I'm writing after all this computation, or after all this derivation, the final conclusion which I can give, that is something else. That is I, this is the imaginary part, iota H bar or H cross. By partial derivative of the wave function with respect to time, it will be equal to minus H caps, like H cross square by 2n, and we have del square by del x square plus del square by del y square plus del square by del z square. Wave function, that is the psi, plus u psi. Now we will look at it. First, let me highlight it. Okay, so let me just bring this. Okay. Just, yeah. No, I can take it. This is what. Now I will help you in understanding this from where we got this. Just a minute. See, the energy equation which we got now, we can do further, like one more kind of a calculation we can do that we are doing now for energy equation. See, what is total energy? Total energy is kinetic energy plus potential energy. What is kinetic energy? Half mv square. V is the velocity of the particle. What is potential energy? We can treat it to be capital U. Now, according to de Broglie's hypothesis, like we can derive it. We have done that. We will discuss it some other day. But we know that energy in the reduced Planck's constant, H cross or H bar, it is a reduced Planck's constant, omega. So this is the frequency, like this is the relationship between the energy and the angular frequency. And why it is important? Because in a wave, angular frequency plays a very important role. Normally we have E is equal to H mu, where mu is the frequency. That's the normal frequency. But we have a one more very interesting relation, this relation, which is E is equal to reduce Planck's constant into angular frequency. And we are making use of that because we are trying to decode or analyze the wave. And in the wave, angular frequency plays a good role. Okay, so this is clear to us. And similarly, what I can do here, I can multiply and divide both the side with m, like numerator and denominator. It will become half m square v square. So half m v square. So p square by n. Let's see. So p square by 2n. And I know that p also I can write like h bar or h cross k. I can write it like half h cross k square by n plus u is equal to. So this is a very important discussion we did. Actually, we did earlier also, but yeah, the idea is that this equation E is equal to half mv square plus u. It is very good in classical mechanics, but in quantum mechanics, we can convert this energy equation into the one which I have written in the last. Let me write it with some bold font so that it becomes more readable. Like I'm just trying to make it more readable. So I have something like this. H cross mu, H cross angular frequency is equal to half. Instead of P, I can write H cross K square upon M plus capital. And here we made a use of two very basic formulas that I will write for reference. The one very important formula which we made use is E is equal to H cross mu and P is equals to H cross This is the basic formulas which we had decided. We got this equation. Okay.
Yes, sir.
Now this equation along with this. So now what I can do is in this equation I can multiply both the side with a wave function. And then I can do the appropriate substitution from here. Like the same we did earlier in the earlier derivation. Then we will get something like this. So this is the main idea which we, okay, like I can give you some idea. Yeah. So just just a minute. Now one very important discussion I have to make. One very important discussion. It's very important, very interesting also. See, uh, from here, like from here to here, you can go. And how we can go, that I have already covered in one of the derivation. The previous derivation which we did. We have seen a way to go from here to here. But now my point is that the equation which we have now, it is not time independent. It still has a t here. When the equation is time independent, when there should not be any t, isn't it? And how we can achieve that? That is the idea. We can achieve that by two techniques we can apply. The first one is that instead of this wave function which we have, instead of this wave function which like this derivative term which we have, we can substitute this equation here, because we have already derived now, we have already shown that partial derivative of the wave function with respect to time, it is phi x into the other term. So here I can do that. Let us do that. So what this equation will become? It will become I h cap and just a minute. Since we have previous work, so let me make you clear. Like from this equation to this, the transformation I was telling, like from here to here, how to go? Let us revise. We can revise. It will take hardly 5 minutes. We can revise. So till here we got. Till here we got. Now see what I did. I multiplied the both sides with the wave function. In this step, I multiplied both the sides with the wave function. Then what I did the proper substitution. How I did the substitution? This thing, omega into psi. This I replaced it with omega into psi. Yeah, this omega into psi. Partial derivative of omega with respect to t upon minus I. Something like that. So or both the sides I multiplied with I. So I partial derivative of omega with respect to t is omega phi. This. Can you see this? This term, so instead of omega phi, I can write this. I partial derivative of psi with respect to t Let us do that. That is what we did here, as you can see. Instead of this omega into psi, I have written this derivative. And similarly, this k square into psi. So k square into psi is minus of this double derivative of psi with respect to x. So minus of double derivative of psi with respect to x. This is what. So we did our proper substitutions, and yeah, and after shuffling it a bit, we got this equation. Now, unfortunately, this equation is not time independent. Huh? It is time dependent because time term is there. And here, what we are discussing time independent because earlier we discussed time dependent. So now our goal is that whatever equation we got, let us convert that into the time independent form. And that is what we are trying to do. So this is the same equation I am making use of here. Same equation, I'm just plugging it here. And from now this equation which we have, we will convert it into time independent. That is what we are discussing. Let us see how we are doing. Let us see how we are doing. So what I am trying to do is that derivative of psi with respect to t, this is this pi x into this, that I can substitute. That I can substitute. Let us substitute. So we will get something like this. Phi x e to the power of I omega t minus I, isn't it? Okay, this is clear. And rest of the equation, I can keep it as it is. Because the rest I am not concerned. My concern was to get rid of this time. So I applied a technique and let us see. So let us keep it as it is. All other terms we can keep it as it is. And this term I can replace it with the Laplacian. That okay, later I will. Let me write it. Because this is the equation in the 3D, three-dimensional space, wherein x, y, and z, all the three axes are involved. It's in the three-dimensional space. Wave function, potential energy and the wave multiplied by the wave. So this is clear to us. Now we are happy that okay, I applied some jugaad, but unfortunately the jugaad we applied, it is still just I'm trying to bring it in the same frame. Let me copy it. Okay, unfortunately this jugaad hasn't worked. Why it hasn't worked? Once again, I am having the t term in the equation. This t term, once again, omega t. I have to get rid of t. Now, once again, I will look at the other equations which I derived. Is there a way to get rid of this t? can I do any substitution to get rid of this t? And here I got one magic. This what result what we got. Now let us analyze this. This can help us. This can help us in freeing this equation from t. How it will do? Let us see that. So whatever I have, I can shuffle it a bit. And how I will shuffle it? I can bring this to this side. Then what will happen? It will become e to the power of I omega t. This will be as it is. And this will be 1 upon del square phi upon del x. Now, like the very basic maths I used. See, we know that now. We know if 1 is equal to e to the power of minus I omega t, if I take this here, it means what I'm doing, I'm dividing it like 1 upon e to the power of I omega t is equal to something like minus into minus. Now I know that 1 by x is equal to x to the power of minus 1. Let me write it properly. It will be 1 itself. And when I take it into the numerator, it will become e to the power of I omega t. I think this basic mathematical operation is clear to you, right? This property there.
Yes, sir.
Okay, very nice. And if it is clear, then to you you agree that okay, we can do like this. Okay, and if it is so, then we have something very interesting. We found something very interesting. And what we found interesting, that I will very soon show it to you. For that, let me make some space. So this is the, so now see, now this e to the power of I omega t is the one which is troubling us, which is not letting this equation to become independent of t. Now, instead of e to the power of I omega t, I can substitute this. And if I substitute it here, then our equation is independent of time. Isn't it?
Yes, sir.
And that is what we are interested in. That is what we are interested in. I H cross phi x. Now instead of this term, I can write the value, or that the substitution is something like this. Double derivative of phi with respect to x into 1 upon double derivative of psi with respect to x. Then I can write minus I omega, and it will be RHS will be same. No need to do it because that is already sorted. No time term is there. That is what we want. Independence from the T. And now what I can do, I can replace this thing with reverse triangle square. And this operator, it is known as Laplacian operator. I can introduce a wave function. Yes. The potential energy and the wave. This equation which we have, this equation is independent. And we achieved that independence using this phi x. The function which we introduced, phi x function, it helped us in achieving this independence. Okay. Now we can, so this we proved. Now we can also discuss the method number 2. There are 2 methods to do this. So now we will discuss the method number. Method number 2. Method number 2 to derive the time independent Schrodinger wave equation. So we are starting with the basic equation which we are already aware of, that is double derivative of y with respect to x is equal to 1 upon v square okay wait we will get to this equation. Let me start from bit more basic. Let us start with some from very basic to this level we will achieve, otherwise you will get confused. So let us start from very basic, that we know that any wave, I can represent it with a very general equation like this. And now you might ask how we are able to write like this. So in our earlier classes, you might have seen what is the equation of a wave or a particle which is undergoing a SHM or any oscillation. What is the equation? Equation is y is equals to a cos, or sine also we can use, omega t plus phi. So this is the equation of a particle undergoing an oscillatory motion. And what is a wave? In the wave, every particle, they are oscillating about their position. Up, down, up, down. They are not, particles are not at all moving in the x direction. They are oscillating in the y direction. So whenever we have a wave, the moving wave, in the moving wave, what is happening? Particles are just undergoing two-flow motion. All the particles at their respective positions. They are doing the up down motion. And hence, any particle you take, it will follow this equation. So now this is very clear to us that we are trying to decode the wave function, and since wave function is a wave, I can start with this basic equation. So this equation, and one more thing we have to discuss. Here, this capital A is the amplitude. And what is the amplitude? Maximum displacement which the particle can take. That is the amplitude. And we know that wave function, it signifies the of the particle wave. Like if an electron is moving, it is emitting a wave. De Broglie, wave nature of particle. If electron is considered as a particle, if it is moving very fast, it is emitting a wave. And what is the amplitude of the wave? Wave function itself, omega psi x. So psi x, the significance of psi x is it represents the amplitude of the wave. We call it like the matter wave or particle wave. In the quantum level.
Okay, sir.
Quantum. Now this is very clear to us. Now we will be applying some basic mathematics to get to some good result. Let us differentiate this with respect to t. Or first let us differentiate it with respect to x. Then we will differentiate it with respect to t. Let me write it. Differentiating with respect to x. When I differentiate this with respect to x, I will get something like this. Partial derivative of y with respect to x, it will be equal to see, cos omega t term will be acted as constant because t will be treated as constant. This I can take this side, like this will be separate. But this psi x, it will be differentiated because it's a function of x. It has to differentiate. I will get some. Now I can differentiate it one more time. What I will get? Cos omega t will be constant as it is. This I will get as isn't it? This is clear to us. Now similarly, we will differentiate the same equation with respect to time. Differentiating with respect to t. That is the time. What we will do. So partial derivative of y with respect to t. Now when we are differentiating it with respect to y, this psi x will be treated as constant. It has nothing to do. It will come out. But cos omega t, it will get differentiated. And I know differentiation of cos theta is minus sin theta. Minus sin omega t, and omega t, I differentiate, I will get omega. So it will become minus omega sin omega. Okay. I can differentiate it one more time. When I differentiate it one more time, once again, this psi x, it will remain as it is. Differentiation of sin omega t will be omega cos omega t. It will become minus omega square cos omega. This is what. Until here, it's clear. Now, I will write one equation. That is a very important equation. That will be the base for us. So I will number this as the equation 2. I will number this as the equation 3. So I took a normal wave equation. I differentiated 2 times with respect to x. I differentiated 2 times with respect to t to get equation 2 and 3. Now I am introducing a new equation that you should remember. It is a basic equation. I am writing that. That is double derivative of y with respect to x is equal to 1 upon v square double derivative of y with respect to t. This I am calling as the equation 1. So this equation you have to remember, like it's a very popular equation. Now what I can do, values of 2 and 3, I can substitute into equation 1. Values of 2 and 3, I can substitute into equation. I will write substituting values of equation 2 and 3 in equation 1. So see what. Now we will get something very interesting, that instead of this double derivative of y with respect to x square, I can write cos omega t into single derivative psi x. It will be equal to 1 by v square and d2y by dt square, that I can write as minus of, or let me write that way only, psi x I have into minus of omega square cos omega. Now see, magic. Now we will see one magic. Cos omega t cancel. Now we have a wave equation independent of the term cos, term t, independent of t. I can bring the RHS into the left hand side to get something very interesting. To get the final equation, basically, I can say that. So, one by v square psi x. Okay. Uh, just if I bring it to the left hand side, this will become plus. I'm just bringing it here, plus, and here I get 0. Okay, and omega square is also there. Sorry, omega square. This is the final equation. And clearly, this wave equation, it is independent of time. Now, just 2-3 things we will discuss. Then this topic will be complete. Small things. Now we can simplify this one very interesting term, omega by v, like omega square by v square we have. Now we can try to simplify this, like convert it into a different form. See, we know omega is equal to 2 pi f. F is the normal frequency. And velocity v is equals to lambda f. So these two basic formulas, using this, what we can get? Using this, we will get something like this. V omega by v is equal to 2 pi f upon lambda f. Ff will cancel 2 pi by lambda. 2 pi by lambda. And what is 2 pi by lambda? 2 pi by lambda is the wave number, like k. So v by the omega by v, we can replace it with k. And so what I can write? So what I can write is, therefore, omega by v is equal to k, and I know momentum is equals to h cross k. It implies that k is equals to momentum by h cross. I can write it. It implies that omega by v is equals to momentum by h cross. Like we are converting, like we are trying to bring in momentum h cross in this equation, so to make it like interesting, useful basically. So with this, I can rewrite it like omega by v. I can write p by h cross. Let us do that. Omega like partial derivative phi s. And the calculation we did. So instead of omega by v, I can write momentum by h cross whole square. And no need to write x because it can be 3D also, no? So just let us write omega like psi itself, wave function. Yes. So this is our refined, like one more form, one more useful form. Because why it is useful? It is containing momentum and reduced Planck's constant in it. And it is independent of time. This wave function is independent. And one last discussion we will do. Now we will try to analyze the energy. We know E is equal to half mv square plus u. I can multiply both numerator and denominator by mass. I will get p square by 2m. I will get p square by 2m plus u is equal to E. Or I can write that E minus u is equals to p square by 2m. Or I can write p square is equal to 2m multiplied by E minus u. And that is what we will be plugging in the equation. Instead of p square, we can plug 2m E minus u. That's it. Let us do this. So now I am doing the double derivative of the wave function with respect to x. Just writing it. Okay. Now see, instead of p square, I can write 2m E minus u. E minus u. U is the potential energy, E is the total energy upon h square. Like h cross psi This is the one more form wherein we have a time independent Schrodinger wave equation containing the energy terms, mass and energy terms. So different varieties of time independent Schrodinger wave equation we derived. We did the complete derivation, as can be seen here. So just a very quick wind up. Like today, like what we did. So time independent Schrodinger wave equation. We started with a normal wave equation. Here we introduced this phi x, the position term, because of which whatever we got earlier, this we were able to eliminate time from here because we have to make this. This is this equation which we are having. It is time dependent. We have to make it time independent, and hence we applied some mathematical techniques wherein we introduced this phi x. We did some differentiation to get some useful terms which we made use to get the equation which is time independent. And method 2 is much more, it is very interesting. We started with a normal wave equation, we did some differentiation, and we took this very important equation and we did some substitution to get equation, Schrodinger wave equation, which is independent of time. And we did different varieties of it. We just played with the formulas, the formulas which we already know, the basic formulas. And we got Schrodinger time independent equations. Yeah.
Excuse me, sir.
Yeah, please.
Sir, in method 2, when we are substituting the value